Good morning. Welcome you all for the next lecture on inorganic chemistry of life. Let us just have a brief recap on the previous aspects that I have covered. Just in the previous lecture, I began with these techniques which are used in the biological inorganic chemistry, bioinorganic chemistry. A list of the same can be seen over there as I have already shown in the previous lecture. Of this, a few aspects I have already completed. The aspects such as the protein isolation purification, something on the CD spectroscopy, something on the gel electrophoresis, and a single crystal X-ray diffraction. I have also completed things related to the microscopy, etc. So, in this lecture and the lecture followed by this, I try to sort of go through the major spectroscopy techniques that I will be that are generally used in the biological inorganic chemistry, or in other words inorganic chemistry of life, because you need to evaluate the reactions that happen in the biological system where the proteins are one of the major portions or cellular material. So, for this you require both the spectroscopy and microscopy methods. Let us look at one of the method here. See, we have methods on absorption spectroscopy, we have methods on emission spectroscopy, we have methods on nuclear spin, we have methods on electron spin, and we also have methods in the nuclear transitions. So, variety of these methods are there, as you can see on the previous ones. The nuclear transition is basically the Moss-Boyer spectroscopy, and NMR and EPR refers to the electron spin and nuclear spin methods. Okay. So, let us start with one on the emission spectroscopy. Okay. So, what is emission spectroscopy? In an emission spectroscopy, you have to have a species which is in excited state, which is in electronically excited state. So, you know, absorption spectroscopy will have the electron transition from the ground electronic state to an excited electronic state. Now, with emission spectroscopy, you look at what happens an excited electron when it returns back to the ground state, and that is what. So, the kind of a emission that occurs that you are looking at in the form of radiation. Of course, there are other ways by which the excited state can be quenched, which is called radiation-less processes, but we are concerned with the radiation process, and this radiation process is referred as the emission spectroscopy, and the one which is very commonly used is the fluorescence spectroscopy. Okay. So, in case of biological systems, the fluorescence spectroscopy can be used primarily for those species which can be easily electronically excited. For example, those amino acid residues having the side chains of aromatic type. We know, we have already seen the aromatic like side chains. You have in the histidine, you have in the phenylalanine, you have in the tyrosine, you have in the tryptophan, etc., etc. So, we have looked at all of these. So, that means all of these are very well suited candidates for studying their fluorescence spectroscopy. Secondly, why they are so suited? Because they are a part of the protein. If there is some change in the protein or dynamics in the protein, then obviously that change in the protein, conformational change in the protein or dynamic change in the protein would reflect on the emission properties of these particular residues. Therefore, monitoring their intrinsic fluorescence emission is an important thing. So, could be phenylalanine, could be tryptophan, could be tyrosine, all of these kind of things. Occasionally, people will also do something called extrinsic one. In the extrinsic one, what you do is you attach certain kind of a fluorophores, a fluorescent moieties, and then study their fluorescence as a function of whatever changes that you bring. Change in the concentration, change in the pH, change in the temperature, change in the viscosity, change in the whatever kind of a changes that occur in the biological system, or when they go from a fluid part to a tissue part, etc. All of these can be. So, that means for measuring the emission spectroscopy, you require fluorescent moieties. These fluorescent moieties could be intrinsic like those present in phenylalanine, tryptophan, tyrosine, etc., or these can be an extrinsic fluorescent species which are attached directly to the protein for studying the protein changes. That can be attached at one end of the protein, or they can be attached somewhere in the middle of the protein or in any portion of the protein. That means protein is modified with a fluorophore, and such a kind of things is referred as extrinsic fluorophores, and those of tryptophan, phenylalanine, histidine, all of these are referred as the intrinsic fluorophores. Okay. So, let us look at one example, a chromophore modification that affects on the fluorescent protein. Okay. So, the emission spectra. So, you can look at one of the case is the emission blue, B stands for blue here, and the fluorescence protein, and then in the second case here the cyan color, emission cyan fluorescent protein, then emission green, G stands for green fluorescent protein, and emission Y, Y stands for yellow. So, emission Y that is yellow fluorescent protein. So, we have different modifications. The blue one gives the emission here, the cyan one gives the emission over there, the green one gives the emission over here, the yellow one gives the emission over there. So, you can see the emission wavelength is shifted, that means emission color is also shifted. So, this can be helpful to study the protein dynamics, protein conformation, etc., by looking at the changes either in the intensity or in the position of the emission, or both in some cases that you can see in all of these. Okay. And let us look at another example, but this example is not just simply based on the emission, but it is based on the excited state lifetime. As I mentioned to you, the emission spectroscopy comes out because there is electronic transition from the ground to the excited electronic state, and this ground to the excited electron state will make the species in the excited state. And now the excited state will not remain in the excited, but that will return back to the ground state. So, return back to the ground state, there is a time taken in this. So, that is what the time taken for this that you study, excited state lifetime measurements. Generally these lifetimes are in microseconds, in the nanoseconds, femtoseconds, all these kinds of things, so 10 power 6, -6, -9, -12, etc., -15, etc. So, in the fluorescence they are there. In the phosphorescence, of course, you know that they are in the milliseconds to even a fraction of a second to seconds as well. So, therefore, we are looking at what is the rate or what is the time. Rate and time are related to each other, rate and time are inversely related to each other. Okay. So, 1 by time is the rate, 1 by rate is the time. So, therefore, it does not matter if I use the word rate of excited state decay, or if I say lifetime of the excited state. So, the excited state lifetime means how long the species sits in the excited state. Okay. So, this is again the lifetime is dependent on various parameters, the parameters of the protein dynamics itself, protein conformation itself, and viscosity of the medium, many other parameters, so pH of the medium, various things. So, all of these will influence the excited state. In some cases it will stay longer in the excited state, in some other cases they stay shorter in the excited state. Therefore, excited state lifetime becomes an important parameter for us to monitor if we want to study the dynamics of the protein. Or not only dynamics, suppose you have a small molecule which reacts with the enzyme. In case of enzymes, what are the small molecules which reacts? In case of the enzymes, it is the substrates. Substrates bind to the enzyme. So, when the substrate binds to the enzyme, there are some changes can occur in this conformation. When the substrate is converted to the product, again there could be some changes in the conformation. When the product is released, there can be some changes in the conformation of the protein. So, all of these conformational changes, or in other words some kind of a dynamics, can be studied by following the excited state lifetime measurements. These are dependent on the various parameters like viscosity, dynamics, conformational changes, pH, various other factors, concentrations, all of these like the ones. So, very nice. So, if you have an enzyme, you want to understand whether the substrate is bound or not, you can study. So, you want to study whether the enzyme has acted on the substrate, has converted the substrate into the product or not, that can also be studied various. So, here I have taken an example slightly different in nature. This example is coming from a protein called I-lens protein. You know that we have several proteins that function in the I-lens, and some of these proteins get modified as a function of age, time. As a human grows, you must have heard some of your elders saying that, oh, I am not able to have a good vision, I am not able to see very well. That is because they have certain kind of a layer, they call it as, which is nothing but cataract. So, the cataract is nothing but, for a chemist, it is nothing but some kind of a modification of the protein. Okay. So, what can modify in the protein? Various side chains can modify in the protein. Some of these can be even glycosylations. So, all of these will modify. When they modify, some of the proteins may join together, may aggregate. So, protein is modified because the side chain is modified. The modified protein is in turn added up together to form a kind of a polymeric species. So, you form a kind of a layer. The individual protein molecules are connecting together. Just is like, suppose you have these lens proteins are like rod like molecules that you have. So, and you have another rod like molecule, and you have another rod like molecule, you have another rod like molecule, etc. So, these are individual lens proteins. Okay. So, these lens proteins, due to the modifications, they get connected to that. So, they get connected to that. So, they are modified in various ways, and these modifications can be explained. Now, this forms like a individual rods are joined together, now form a kind of a layer which we call it as a cataract formation. So, this is what is the disease, and we as a chemist can identify such kind of things. So, you can identify such things because when it is modified, any of the thing is modified, you can see that the modified portions, their dynamics is different, therefore lifetimes are different. When they are connected together, the lifetime will also change. So, here we have shown some example when some modifications are brought here. As you can see in this particular lens protein, some modifications, simple tryptophan, hydroxytryptophan, arginine P, variety of these modifications. It is not necessary what these modifications are at this time for us to know. All that we know is that these amino acid side chains are modified. Some of these modifications will lead to the aggregation phenomena. So, the protein to protein, rod to rod can join, like the way that I have shown you here, and these are all joined together and to form a kind of a layer. So, such kind of things can be studied. So, when the modifications can be studied because they shift in their emission, they also change in their emission pattern in terms of the lifetime. So, all of these things are referred as the lifetime decay curves, and these decay curves are generally fitted to exponentials. It can be 1 exponential, 2 exponential, 3 exponential, that is monofunctional, bifunctional, trifunctional, etc. So, these are some of the things that we can. So, we can resolve these and get the lifetime measurements, and the lifetimes will vary as a composition of what kind of a changes have taken place, to what extent they have taken a place in this. So, I think this much of a message is good enough. So, that means what I would like to say is, using the emission spectroscopy, using the excited state lifetime measurements, you can study very clearly the binding of the substrate to the protein or enzyme, the reactivity of the substrate to convert to the product, and the changes that occur in all these, and all of these kind of parameters, or changes in the pH, changes in the dynamics of this, or temperature, everything can be monitored. So, very well. So, that is one of the very vital technique. Now, let us smoothly switch over to another technique, Another technique is mass spectrometry. What is a mass spectrometry? Mass spectrometry is based on the mass. So, mass of a species, mass of an ion, a mass of a molecule when it is converted into an ion. Okay. So, therefore, you convert the molecule into an ion and you measure that. So, from that you can get the mass of these. Okay. So, the molecules are converted into their ions and these ions are measured. So, more details of mass spectrometry I am not giving here, the instrumental details, but I would give details of how it can be utilized. So, there are a large number of mass spectrometry methods are there, of which I am talking to you about two other techniques. One is ESI, electrospray ionization mass spectrometry, and the other one is called MALDI. What is MALDI? Matrix assisted laser desorption ionization. Matrix assisted laser desorption ionization spectroscopy. Generally for smaller size peptides, molecules, you can use ESIMS. For bigger size proteins and huge molecular weight proteins, they are all studied by MALDI spectroscopy. And both of these will not bring much of a breakage in the molecule, but just makes a soft ionization. These are all soft ionization processes in that. So, so in this you have a electrospray, which is a solvated electron which gets added to your molecule and convert into a species, ionizable species, and that species you are measuring. In the other you have you mix your compound, a molecule or a protein with a matrix protein. It is a matrix which and then shine with a laser light, and the laser light is absorbed by the matrix and then transfers this energy to the molecule, and then as a result of that molecule gets ionized, molecule gets desorbed and ionized. That is what you study in the MALDI. So, here is some example. As I told you, and you know very well, in mass spectrometry you basically have a piece of information of importance is that what you measure is m by z. Okay. So, you measure m by z. Okay. So, z is the charge. So, this charge can be 1, it can be 2, it can be 3, it can be any number. So, if it is a negative charge, -1, -2, -3, if it is a positive charge, +1, +2, +3, etc. So, that means the peak position is peak position in mass spectrometry, MS spectrometry is referred as the m by z. So, in that the z it refers to the charge. So, if you want to get the mass is equal to the peak position in the spectrum multiplied by z value. So, this will give actual mass. So, this will give actual mass. So, this you will find in the spectrum, from the spectrum, and you can also find the charging. So, therefore, you can get the mass of the species. So, this is an important thing. Now, here there is some example is taken over here. Okay. So, it is not very important what this example is, but this happens to be the cytochrome C. Cytochrome C, just take as it is and put into the electrospray ionization mass spectrometry, you get one peak for the 9 charges. So, whatever the value you get multiplied by 9 will be the molecular weight of that particular thing. Now, as I said that the Z can be played with. So, the Z means can be charges can be added, can be removed. This can happen by adding a charge, for example. So, you can add the charge by adding some kind of a acid to that. Okay. So, so you add acid medium, there is for example trifluoroacetic acid. Okay. So, trifluoroacetic acid, which is TFA, this will add charge H plus to the protein. So, this will add H plus to the protein. So, therefore, that can be really understood. And now you see the spectrum here, compared to this you get more number of species. So, species with 9 plus and 11 plus, 13 plus, 15 plus, 17 plus, etc. And then you can also charge a lot. So, then you can see much more charge, like even 22 plus, 25 plus, etc. All of these kind of things are there. So, one of the things that we learn from this is simple protein may not be able to solve the structure, solve the mass of this particular protein. Then you add some acid that will basically denature, and to this denatured protein you can add more and more H plus, and then more and more H plus will add to Z. So, Z value increasing. So, Z value can become 1, can become 2, can become 3, can become 4. Here we have even 11, 13, 15. Here you have 22, 23, etc., 24, all these kinds of things. So, from this you can resolve and get the protein mass in that. You can also make some changes in the instrumental parameters, can get a little bit more ions to 11, 13, 15, 11 plus charge, 12 plus charge, 13 plus charge, 14 plus charge, 15 plus charge. So, what we understand from this? We understand from this, when you have a protein has side chains. You have seen carboxylic groups, you have seen phenolic groups, you have seen amine groups, you have seen amide moieties, you have seen many kind of groups are there. So, these groups you can either add a proton, imidazole is also there. You can add a proton, you can remove a proton. So, when you add a proton, you are adding one mass plus one charge. So, addition of proton is one mass added plus one charge added. So, that is how you need to calculate and get the corresponding thing. So, now you know how many charges you added, how many protons you added, etc. From that you can make out. So, this is possible because there are a lot of side chains in the protein which can absorb or take protons. So, can be protonated. So, can be protonated by some extent, by more extent, much more extent too. This is one other technique which is very commonly used for the ESI-MS aspect. The other technique is the multi-assisted laser desorption ionization. You can see one of the example is shown for a small peptide 1, 2, 3, 4, 5, 6, 7, 8, 9 a peptide, a 9 amino acid peptide. As you can see that the corresponding peaks are obtained over here. In this case also you can resolve the peaks into different charged, which I will show you on the next slide, but you can see that this particular thing basically one can study the mass out of these ones. Okay, in the next slide here you can see the MALDI for two proteins. There is one on the left side, one on the right side. The one on the left side is MET interleukin, is a protein, interleukin 2, a protein whose molecular weight is 15,549, that means around 15.5 kD, kilodalton. We refer generally as a kilodalton. Okay. So, protein molecular weights are generally in kilodaltons. Protein molecular weights in kilodaltons. These are referred as kD. Okay, kD. So, you will have 5 kD, 10 kD, 50 kD, 100 kD, 200 kD, 100,000 kD. There are proteins of all these. Now, here you can see that interleukin 15,000, you have a peak for 12 charges, 13 charges, 14 charges. Using more than 2 or 3 of these, you can solve the mass for this one. And here bovine serum albumin, it is a huge protein because it is a tetramer. So, bovine albumin is a tetramer. It also can be called as a bovine serum albumin, and its molecular weight is 66,300, which is called 66.3 kilodalton. And you can see but that means more number of residues, more number of side chains, so therefore more charges is possible. Here you will have about 150 to 170 amino acids, here you will have 650 to 700 amino acids. So, obviously, the thing is increased by at least 4 times. So, the molecular weight of this 15,000, 60,000 about 4 times. You can see the charges 14, 15, 16. You can see here 55, 60, 65. So, everything is increased by 4 times. The number of residues are increased by 4 times, the mass is increased by 4 times. The charge species, these are all Z values. Z value 50 plus, 55 plus, 60 plus, 65 plus. So, using this you can solve the mass of this. Now, let me tell you which I have not shown in the slide. When you do in the earlier slide, I have shown that the people isolate the proteins from cells, from other materials, etc. When you isolate, you purify too. At certain stages of initial stages of purification, the protein what you want is there, also some other proteins there. How do we know that so easily? So, you can use the MALDI technique, because the mass of those impurity proteins is different from the mass of the actual protein. So, therefore, from the MALDI you can find out the protein impurity too. So, isolated proteins purify, then you get a pure protein. This can be evaluated by purity, can be evaluated by MALDI. So, you can find if there are some impurities, what kind of impurities, everything you can find. Excellent kind of a technique that you have. So, let us see the next part of it is the mass spectrometry. Then we go to the NMR spectroscopy. So, let us look at the NMR spectroscopy. We are very familiar with NMR spectroscopy. What is NMR spectroscopy? Nuclear magnetic resonance, that is nuclear spin of the nucleus having the spins of plus half. Nuclear spins, or it can take plus half and minus half too. Okay. So, therefore, these two under magnetic field, these two having same energy outside the magnetic field. So, let us say plus half and minus half, and you apply a magnetic field. So, these are in the magnetic field, these are split into the plus half into minus half. Okay. So, the species which are present to the other, this is the transition. So, in other words, you cause a nuclear spin transition going from one kind of a spin to the other spin, that will result in the nuclear spin transition kind of a technique, and this requires energy, and this is in the radio frequency. This is the h nu is equal to h nu. So, by supplying that kind of an energy, you can cause the transition. Generally, in the NMR, in the diamagnetic means organic molecules, if you take their proton NMR spectrum runs somewhere between let us say proton 1H NMR of diamagnetic goes from 0 to 15 ppm. Okay. Whereas, when you have some species such as when you have some species such as a paramagnetic species, when you have, and these the shifts the NMR spectral they shift in the under the presence of the paramagnetic species, under the presence of the paramagnetic species. So, the paramagnetic species shifts the chemical shift position O known as delta. Okay. So, the delta can be changed. The other parameter that can also shift is the relaxation time. And in metalloenzymes, you know, there are a lot of metal ions are involved, transition metal ions, and these transition metal ions are basically have, some of them will have the paramagnetism. So, therefore, one can easily make out structures by using this such kind of a paramagnetic species. Here we have taken one molecule, the phenanthralene, the complex of the cobalt 3 plus, but the cobalt 3 plus here is D6 where all electrons are paired, and this is diamagnetic. So, in this diamagnetic kind of a system, then you have a you have no shifts happening in this, and therefore, you get the spectrum very small in region 0 to 10 or 0 to 15. But instead of the cobalt 3, you take cobalt 2. So, the cobalt 2 is paramagnetic. Now, you see the same set of peaks have spread to almost 110 ppm. From going from 0 to 10 ppm is going from 0 to 110 ppm, and that is what is called the paramagnetic shift. So, this is called the paramagnetic shift or the contact shift. So, this is a boon in disguise, you know, because in metalloproteins the metal ion is connected to different side chain residues of the protein, and therefore, those residues where it is connected directly, and if the metal ion is paramagnetic, they can be shifted here too. Okay. Just an example is shown over there. You take some hexanol and add some shift reagent, which is a europium compound. In the simple hexanol, everything is within 5 ppm, and hexanol with the europium complex, that you see it goes much downfield, and each of the CH2 group can be separated out, one CH2, other CH2, other CH2, other CH2, other CH2. Okay. So, in effect, what I would like to say is that the paramagnetic NMR generally organic chemist thinks is a curse, but for a bioinorganic chemist, biological inorganic chemist is a boon, and the paramagnetism will shift the spectrum, and as a result of that we can get the different things resolved. And in the next class I will demonstrate one example of this and then explain you much better. So, yeah, thank you very much.